Okay, let's continue with second part of switch level modeling. In previous lecture, we have studied unidirectional switch primitives, particularly NMOS, PMOS and CMOS. These switches, it is assumed that current is flowing in one direction only. That is true for simulation purpose. In real switch, current can flow in both directions. If in your design you need bidirectional switches, then you have to use bidirectional switch primitives. So there are three types of bidirectional switch primitives: tran, tran if 0 and tran if 1. Tran switch don't have any control input, hence it is always in a conducting mode, whereas tran if 0 switch will conduct only when control input is logic 0, and tran if 1 switch will conduct when control input is logic 1. Syntax of these three switches are shown in the presentation, where instance name is optional. Okay, now let's see some examples of these bidirectional switches. Let's start with a design of 4:1 multiplexer using bidirectional switches. Here we will use tran if 0 and tran if 1 switches. Let's understand the schematic first, and then we will see the Verilog model. As you can see in the schematic, selection input S0 is connected to switches in the first level, and selection input S1 is connected to switches in the second level. Now when S0 and S1 both are 0, then both tran if 0 switches in first top row will be on, and thus input I0 will get connected to the output out. Now when switch S1 is 0 and switch S0 is 1, both switches in second top row, that is tran if 1 and tran if 0 switches will be turn on, and input I1 will pass to the output out. In this way, when S1 is 1 and S0 is 0, input I2 will pass to the output, that is out, and when both selection input S1 and S0 are 1, then input I3 will get connected to output out. One more thing is, same design can work as demultiplexer also, as we are using bidirectional switches in the design. Thus when selection input S0 and S1 are 0, signal out will pass to the I0. Only the change required is out has to be defined as input and I0 will be output in this case. Same way it will work for other selection input combinations. So the same design can work as a multiplexer as well as a demultiplexer. Now let's understand the Verilog module. First, inputs and outputs are declared. Here we need for intermediate wires, four intermediate wires T0 to T3, which are declared with keyword wire. Now see, first tran if 0 switch in first top row has input I0, output T0 and control input S0, which are written in bracket for first switch. Similarly, second switch tran if 0 in first top row has input T0, output out and control input S1 written in the bracket, with second switch in first row in the code, and so on. Okay, now let's say test bench for this multiplexer. Here we have instantiated our multiplexer module, then define all 6 inputs as reg and output out as wire. Integer k is defined to generate integer numbers from 0 to 63 because we have a total 6 inputs here. So we have to generate a 64 input combination. For loop is used to generate all 64 input combinations. Then display statement is used to display 2-bit selection input followed by 4-bit input I and 1-bit output out at the end. So on this slide you can see simulation results for selection inputs 0, 0 and 0, 1. Input I is varying from 0, 0, 0, 0 to 4 ones, that is 1, 1, 1, 1. Continued with simulation result from the previous slide. Now for selection inputs 1, 0 and 1, 1. You can see the result in this slide. Now let's see little more complex design. Here we are implementing full adder using switches or transistor. So you can see top level full adder module at left hand side, in which we have instantiated sum and carry modules. Now at the right hand side, carry module is written, which we are implementing using 6 NAND gates N1 to N6. You can see this gate level circuit in the presentation. Okay, still design hierarchy is not complete. CMOS NAND gate has to be implemented now. So this module we will implement later using switch level modeling. So we just completed the carry logic implementation. Now let's see how to implement some part of the design or adder. So as shown in the presentation, in the left hand side code at top left, at top level, some logic is implemented using 2 XOR gates, X1 and X2, whose netlist or circuit is shown at right hand side. Now we have to implement this XOR gate. So you can see in right hand side code, XOR gate module is implemented again using 5 NAND gates N1 to N5. Its netlist or circuit is shown here in the presentation. So in this way we have implemented sum as well as the carry logic of full adder using NAND gates as seen in the previous slides. Now we have to implement this NAND gate. So you can see on this slide we are implementing this NAND gate using NMOS and PMOS switches as shown in the circuit. We have already seen this switch level modeling of NAND gate in a previous lecture. So this way we have completed modeling of full adder using switch level modeling. Let me summarize how we have implemented this design in a hierarchical manner. First, top level adder we have implemented using 2 modules, sum and carry. Then carry module we have implemented using NAND gates. Sum module we have implemented using 2 XOR gates. Then XOR gate we have implemented using again NAND gates. And finally NAND gate we have implemented using NMOS and PMOS switches. Hope you have understood the design structure and its netlist. So here we have a test bench and a simulation result for full adder design which we have just designed. You can see we have instantiated top level module which is full adder FA here with A, B, C in as inputs and sum and C out as outputs. For loop is used to generate 8 input combinations, and finally all inputs and outputs are displayed by using display statement. Okay, so now let's see different data values supported in Verilog language. So logic 1, logic 0, X which is unknown, and Z, that means high impedance, are the supported logic levels in Verilog. If any net is floating, then it is initialized to high impedance by default, and all register variables are initialized to unknown, that is X. Okay, this table shows signal strengths of different data values in the increasing order. Supply, that means logic 0 and logic 1, has highest signal strength, whereas high impedance Z has the lowest signal strength. There are other data values and their signals values in between. If two signals are driving same net or wire, then signal which has a highest signal strength will prevail. For example, if logic 0 and high impedance are driving one wire, then logic 1 will pass on that wire, or logic 1 will dominate. Data values and signal strengths are very useful, particularly when we use transistor level circuits. When we use resistive switches, signal strength decreases at the output end. Data values and their signal strengths are not required to discuss in detail in this course. Okay, so point to note here is switch level model in Verilog cannot be synthesized. So here we have finished switch level modeling. Hope you understood the topic. Thank you.